All right, so this is the deal right here, and it says that the blood itself, which is located in the test tube right there, is going to be spinning around, and it can't separate blood until it's 500 times the acceleration of gravity. So that has nothing to do with rotational kinematics. That is a centripetal acceleration problem, and I want to encourage you to remember that we have more than one way to deal with the centripetal acceleration. So I'm going to find the rotational speed. I'm going to find the radius necessary to get the blood up to 500 Gs, because it says 500 times the acceleration of gravity. That's 500 Gs. And that has to equal omega squared R. Now, in the prior example, or in the prior problem that they refer to, they say that the centrifuge spins at 1200 RPM. So that's going to be our omega here. But to use omega here, it's got to be in radians per second, not rotations per minute. So the first thing I'm going to do is take my 12,000 rotations per minute and convert it into radians per second. I will need some help with this, because although it's 2 pi radians every rotation, and it's, let's see, we gotta go to seconds, so 60 seconds in 1 minute. So we gotta multiply that sucker by 6.28 and divide by 60. So I'll give you guys a second to do that while I get this thing off and put this one on. All right, so that should be enough time. So Rachel, since you asked about it, I'm sure you did that conversion for me. You got 1,256.6 squared. So that's now in radians per second. And this is 5,000, and this is R. So this is going to give us the radius necessary for the blood to be at. And we're saying it's got to be somewhere around here in order for it to separate correctly. So whatever the result of this is the radius. And just to be clear, this side is in meters per second squared. And this term is going to be in radians squared per second squared. But radians is not a real unit. It's not a unit in the traditional sense. Squaring it, cubing it, none of that matters. So radians is actually unitless. So it doesn't count. So when we divide this out, all that happens is the second squared cancels, telling us that whatever answer we get is going to be in meters. So you should work it out to get the number, because I don't think that number actually matters that much, does it, for the next part? I don't know. I have to read the next question. The blood must be slowed down to rest over a long period of time in order to keep the blood separated. It can take a total of 10 minutes for the centrifuge to come to rest. What is the radial acceleration and angular displacement of the centrifuge? And how far has the blood traveled as it slows down? Okay, so we will need this radius to do the next part of the problem. So I'll let you guys figure out what that radius is while I set up the next part of this problem. All right. So my initial velocity is this 1,257 radians per second. My final velocity is going to be 0. They say 10 minutes, that is 600 seconds. And we want the angular acceleration and we want the angular displacement. So we also want the, we also want the linear displacement. So these are all the things that are being asked of us in this final part. Based on what they've given us, I see a pretty straightforward path to getting all of this. To get the angular acceleration, I'm going to use an equation that has these 4 things in it. And that's going to be alpha equals omega final minus omega initial divided by t, or 1257 divided by 600 seconds. And it's negative because it goes to 0. And that's about -2 radians per second squared. It's a little more than that, but I think we can be okay with that. Again, it's not about the numbers so much. Delta theta, on the other hand, I'm probably gonna have to use 2 alpha times, no, I don't wanna use that. I wanna use 1/2 omega final plus omega initial times t. That's what I'm gonna use. And this is a lot, because it's gonna be 1/2 0 plus 1257 times 600. So yeah, that's a lot. That's a big number. It's a big boy. And you can't see it anyways because my head's in the way. So I'm sure somebody's going to knock that out of the calculator and tell me what it is in a minute, because Lord knows I'm not going to do it. 376,980 radians. So if you want to figure out how far the blood travels, you got to take this and multiply by whatever you got for R here. And that's how far the blood travels in meters. That's a long way, but I'll remind you, if you want to convert any angular measure into a linear measure, you have to multiply by the radius, but you have to be in a unit of radians in order to do so. So does that give you enough information for number 5? Number 5 does all of the things I would ask you to do on a pop quiz tomorrow. I would probably ask for maybe fewer of those things because I want the whole thing done in like 10 minutes, but I'm going to ask you to do something like this tomorrow. Is there another one in here that you would like me to talk about? Yes, ma'am. Number 1. Aren't you in my research class? No, not at all. I just don't know why you didn't ask me yesterday in research class. That's a good reason. Of all the reasons you could have said, that one's good. I'll take that one as that's the right answer. All right. And you know what I say to that, right? You should expect more from your teachers. You should. Someday, maybe before you graduate high school, you'll have a good teacher. It's just not going to be today. All right, number 1. Now I gotta move myself yet again. Why do I even keep a picture of me on here? I know why I do, because that's how vain I am. It's got to be a picture of me. That's right. All right, it says a bicycle is ridden from rest to a speed of 20 miles per hour, 9 meters per second in 12 seconds. If the wheels have a radius of 0.25 meters, how fast are they rotating at full speed in radians per second? And how many rotations do they make in getting up to full speed? And what is the angular acceleration while getting up to speed? And how, basically just ask for everything. All right, Mr. Shelton, why would you do this? Because I'm a terrible person and I want you guys to suffer. Look, there's like all of these different things here and it wants like lots of these. So I'm just gonna write them all out so I can help myself keep track of what's being given and what's being asked. And again, a reminder that if I want to go from one side to the other, it just has to do with the radius, which we now know is 0.25 meters. All right. So here we go. They tell us that the bike goes from 0 to 9 meters per second in 12 seconds. All right. I rode my bike this morning. I can tell you, it was cold. My hands are still like cold, but I got my coffee here to keep them warm. You don't care about my plate though, so let's keep going. We want, if the wheels, how fast are they rotating at full speed in radians per second? All right. How many rotations do they make? Okay. And what is the angular acceleration? Okay. And how far does the bicycle travel? So I have to find something for each one of those question marks. So I think one of the easiest ways for me to do this problem would be to I'm just going to do everything in terms of well, I'm going to convert this one. That's what I'm going to do. I'm going to convert that to angular. That seems like the best way to go. Presents. It's not presents. They're empty boxes. I gotta send lab materials home to the kids in E&M. So they sent back their empty boxes. Wasn't that nice of them? So I'm going to use V equals omega times R to figure out what omega is. So I'm going to divide 9 by 0.25, which is like multiplying by 4. So this is 36. So I got the first answer down. I need delta X. I can get that from the information that's here without having to convert to any kind of rotational. I can use a motion equation that has those things in it. So let's do that first. Delta X equals 1/2 times V initial plus V final times T. That's going to be 1/2 times V initial, which is 0, V final, which is 9, times T, which is 12. That ends up being half of 12 is 6. 6 times 9 is 54 meters. So delta X is 54 meters. I mean, you could use your calculator. You probably should, but I don't want to. 54 meters. So if I want to find the number of rotations, well, the first thing I could do is I could find the number of radians just by doing the conversion we talked about here. So I'm going to do find the number of radians first. And that's going to be take 54 and multiply by 4. That's going to be 216. Please tell me that's right. Great. So now divided by 2 pi, which I'm not going to do. So divide by 6.28, and that'll give us a number of rotations, which I don't know. I was watching Jacob not do it. Do you know how many rotations it is?
I got 34.4.
34.4. Okay. I'm going to take your word on it. Somebody else get 34.4 just in case he's not right? Yes, sir.
Does theta have to be in rotations or can it be in radians?
Well, because Mr. Shelton wrote this problem, I'm pretty sure he made you convert. It says how many rotations do they make in getting up to full speed? So yeah, that's kind of a jerk move by Mr. Shelton, but he's trying to make sure you can do it. So yeah. One more question mark left, and that's the angular acceleration. So that's still 12 seconds. I think, let's see, I think we'll just use alpha equals omega final minus omega initial over T. I think that's the best way to go. And that's going to be 36 minus 0 over 12, or 3 radians per second squared. Woohoo! How's that?
I don't understand how you got the angular one. The angular, yeah, the 216 to the 34.4.
Do you understand how I got the 216?
Yes.
Okay, so I just divided by 2 pi. It's 216 radians. I didn't do this whole thing. I should have. To do my conversion, I need my conversion fact. So radians and rotations. So my conversion fact is that for every 1 rotation, there are 2 pi radians. So I divided by 2 pi, so 6.28. But I divided by 2 pi. I didn't divide by 2 and then multiply by pi accidentally because I can't figure out my calculator. Actually, I counted on Jacob to do it correctly. I think he did, though. It's a much smaller number.
I have a quick question about that part.
Good. I love questions. I live for
So, when you solve for that 216 radians, when I put everything in the formula, let me see. So that final velocity that's in meters per second, you're multiplying it by time, which is in seconds. So wouldn't that just give you meters?
Where are we talking about? I'm sorry.
The part where you're finding that delta theta there, the 216 radians. Oh, wait,
Um,
maybe I'm on the wrong thing, actually. I think I'm looking at something else.
okay. Because I didn't use a motion equation to figure out delta theta. I converted directly from this number by using delta x equals delta theta times radius. And the radius being 0.25 meters, it should cancel the meters out when I divide, leaving me with a unitless quantity, which implies radians.
Oh, I see. So, oh, I know what I did wrong now, because for some reason I initially, like in the first section of the question, like before doing anything, I already did it in radians per second, but for some reason I thought I left it in meters per second. So I see what I did wrong now. Okay.
Alrighty, no worries. I'd argue this is exactly what I would expect you to do tomorrow too. The only thing missing from this, and it's not something that is subtle to me, I think that I need to be mixing this stuff in. We're traveling in a circle. Seems to me like that should be something I should throw down in there. So I get all the circle stuff in there, all the circle stuff I can possibly put in. So I would probably skip one of the pieces here and make you figure out some centripetal acceleration piece. And yes, ma'am.
We go over number 4.
Look, I could do all of them, but I'm not going to. I'll do number 4 though. I'll do part of number 4. I'll at least set 4 up. But hold on. Rachel has something to say.
So this is just like a conceptual question, I guess. So the column on the left is linear, and column on the right is angular.
Yes.
And if they give me like a v or a delta x, I can just multiply by the radius. Well, like I set its equivalent in angular times the radius, and I would just divide it by the radius.
As a blanket statement, yeah, that's true. I want to make sure we understand each other though. This works because the wheel is rolling. So it's rotational and linear motion are linked together because it's rolling. In the prior example, it worked because we were talking about what happened to the blood and where it was on the wheel. So it worked there too. You have to make sure that the problem is asking about something that is attached to the radius, that the circular part of that problem makes sense. You can't blanket say that I can always convert to rotational. Like I can't say that if I push a box across the floor and it goes 10 meters, I can just divide by its radius and get how many times it rotated. No, that doesn't make sense. So you have to make sure there is a clear connection between the rotational part and the linear part, and that you know what that rotational connection is. In this case, the radius of the wheel. But yeah, you can do that at all you want. Did I answer your question? All right, so let's look at number 4, get it set up, and then I'll see if I'm gonna do the whole thing. A merry-go-round has a radius of 2.5 meters. Good morning. Starting from rest, a child runs around the outside of the merry-go-round in order to spin it up. Anybody ever been on a merry-go-round? Anybody been in charge of torturing the kids that are on a merry-go-round? You have not lived until you've been on the delivering side of giving kids joy on a merry-go-round, because joy turns to terror in a moment's notice if you do it right. Yeah, I've been on both sides. I've been on the side that's been terrorized, and I've been on the side that has delivered the terror. And yeah, those are good times. I would encourage you, if you can find a merry-go-round in your neighborhood, to set up shop there one day. Wait for the little kids to arrive, because they will, and encourage them to get on the merry-go-round and promise them that you'll spin it. Your day will turn into fun. I promise. It will be fun. So anyways, let's talk about it real quick. It says a merry-go-round has a radius of 2.5 meters. Merry-go-round, radius, 2.5 meters. Starting from rest, the child runs around the outside of the merry-go-round in order to spin it up. They reach a speed of 12 meters per second. I'm seeing a connection between their linear speed and the angular speed. Are you seeing this connection? This is mostly answering Rachel's question. That at this point, their linear speed, which I would actually call their tangential velocity, if I wanted to be super, super strict about it, is 12 meters per second, but they are causing this to spin. So I think we know the angular speed of the merry-go-round, because I think we can say that the current speed is 12 meters per second. So the angular speed is going to be related by that 2.5 meters. So I figure if I divide the 12 by 2.5 meters, I'm going to get the angular speed. And let's see, that's like, I don't know, is that 4.8? So now we have this angular speed. All right. In 5 seconds. Okay, so this is the final. Initial was 0. Just putting all the pieces together. And the time was 5 seconds. All right, building a bit of a profile here. Not S, 5, then S. All right, what's next? What was the rotational speed of the merry-go-round when the child reaches its maximum speed? Got that. What is the linear acceleration of the child? All right, that'd be finding A over here. I'm not going to do that. 12 divided by 5, you can do it. And then the child jumps on the edge of the merry-go-round. They sure do. What is the centripetal acceleration required to keep the child traveling on the merry-go-round? Oh, fantastic. Centripetal acceleration is a radial acceleration. This is a teachable moment. This is a moment where you should probably write things down. I know you don't think you should because you'll remember everything. And then tomorrow I can prove you wrong. Even if I say analysis, that's why it's so easy to say, yeah, you can use your notes. They're useless to you. You don't write anything down. This kid actually has 2 accelerations at the moment they jump onto the merry-go-round. 2 accelerations. They are accelerating themselves in what appears to be a straight line because they are increasing their velocity to 12 meters per second, which means there is an acceleration in this direction called the tangential acceleration. That is a result of whatever you got when you did 12 divided by 5, which I'm sure you got is 2.4 meters per second squared. This represents the tangential acceleration, the acceleration that caused their linear velocity to change. But they're running in a circle. Even when they jump on, even before they jump on, there had to be an acceleration this way, the centripetal acceleration. This was what was causing them to turn while they were speeding up. They had 2 accelerations. This is, although we say centripetal acceleration, this is often referred to as a radial acceleration. Learn that word. Radial accelerations cause you to turn or change direction. Tangential accelerations cause you to speed up or slow down. They're not the same. That means that there's a total acceleration in this direction. They actually accelerated at an angle. This is a little bit on the old complicated side, but I don't think it's beyond you to understand that. That's why if you've ever run around the outside of a merry-go-round, it's sometimes complicated, especially as you're speeding up. So either way, this part is going to have to be v squared divided by r or omega squared times r. We have both of them, so it doesn't really matter which one of these we choose to use. Just pick one and go at it. So 12 squared divided by 2.5. That's 40 something, maybe. It's 144. Yeah, I don't know. I don't care. I don't care enough to do the math in front of you. Just tell me the number.
You sure?
Yeah,
You're off by a little bit.
that's fine.
57.6.
Okay. That's why I knew I was going to be off. That's why I figured it's no problem asking you. You got your calculator right there. Now, clearly you said 57.6.
Yeah, I did.
Yes or no?
Yes.
Are you sure, Andrew? I mean, I don't want to get this wrong. People are watching me.
Am I sure?
He doesn't know. He didn't do it. Look, the pressure's on you. Deliver.
Yes.
144 divided by 2.5. That seems reasonable.
Yeah,
Okay, then why are you second guessing yourself?
I'm not sure.
Gut up and say, yeah, I believe in myself. Come on, you can do it. I believe in, well, a little bit. I believe in you a little bit. 57.6 meters per second squared. Final answer. All right, so yeah, is that enough, Dahlia? I don't want to do this anymore. Good, good. Tomorrow you'll get to do it. We'll see how smart you are tomorrow. You'll be really smart. I'm very excited about tomorrow. Oh, good, good. That's what I was wanting to hear. All right, so we're gonna do something. You were supposed to find the mass of the meter stick. Did you find the mass of the meter stick? Was it hard? I am confident that some of you did. I am confident that a bunch of you did not, because you just leave the classroom and like, finally, physics is done. Can't wait to get the hell out of here. But there are a few of you who I know worked on it, because in research somebody asked me about it. I'm not going to say who, but it was him, and he asked me about it. So we're trying to figure out the mass of the meter stick, and we got it to a balance point. Can somebody, because I did this in 2 different classes, and of course I didn't really write anything down at the end of class. Can somebody tell me where I put the bracket? Where was the balance point? What? 0.9? 49. No, that's right. That's where the middle of the meter stick was. The middle of the meter stick was 49. Where did I shift the thing to? 39. So this was 39. And where did I put the 200 gram mass? 35. 34. What is it? 34 or 35?
You said 34.
Is it 34 or 35? Okay. So those are all the places where it was. We were trying to figure out the mass of the meter stick. So this is a balance of torque question. If you didn't do it yesterday, then I am sad and mad at the same time. But it's okay. I kind of want to walk through it real quick, but I think you can set this up. I've kind of given you all the pieces that you need. There's a torque arm in this direction for the one mass, and there's a torque arm in this direction for the mass of the meter stick. The first thing that should be in your notes here is that an object that has mass will act as though its entire mass is concentrated at its center of mass. That word, center of mass, we have talked about once before, but it's been a long time. The center of mass is where we can say the mass of the object is concentrated. We know that it isn't, but mathematically we can treat the center of mass like that's where all of the mass of the object is. So it's a mathematical construct. Just so you know, if you're trying to keep notes here, and I know Mr. Shelton does not make that easy, keeping notes, the whole thing, because I'm all over the place. But as a definition goes, the center of mass is a location. It's not a mass, it's a place. I know that sounds ridiculous, but a lot of people begin to get confused about it. So when I tell you that the center of mass of an object is located, and I give you the answer to that, I'm telling you a location. Yesterday, we balanced the meter stick and it balanced at 49. That suggests that that's where the center of mass of the meter stick is. None of these meter sticks are perfect. They all have a balancing point somewhere around 49 to 51. That's the center of mass. It's a location. So that also suggests that the weight of the meter stick acts as a torque at that location. That's why the first time we did the balancing act, I put the clip right at the center of mass to kind of remove the meter stick from the problem. It had a torque arm of 0, so it did not apply a torque to itself. But now, because it's off center, there is a torque arm length, and the torque arm length appears to be 10 centimeters. That means it does apply a torque to itself, causing itself to rotate. We provided a counter torque by placing the 200 gram mass, apparently 5 centimeters away from the balance point. That's the math that I see. Is that the math that you see? So you should be able to figure out what the mass of the meter stick is. I'll give you a moment. You're just working the problem just like yesterday. Yesterday, we were looking for where to put the 100 gram mass. Today, you're looking for what that mass actually is. And in good faith, I will give you a minute to work it out before I randomly call on one person, and it won't be random. I just want to pick on somebody. So, oh wait, I have a roster. It will be random. I am choosing who this will be now. I have my choice. The 60 seconds is off down to 45 seconds. Down to 30 seconds. I've given you some information, some clues perhaps. But I'm still picking on somebody here, and I've gone over my minute of time. So funny because it's one person away from Andrew.
Oh my God.
One person away though.
He didn't know that.
Well, I didn't know. I just dropped the pen.
But he didn't know that.
No, but now he does. But it's Anthony. Anthony, did you get an answer for me? Okay, I'm patient though. But Anthony, I'm going to pick a backup person because you don't have it yet. That way, in case disaster strikes, I got somebody else.
Okay, that was at the top.
I have my, oh, it landed on the line. I have two people now. And they are both here. Well, I mean, they're both present in class today. One of them is over there and one of them is out there. But hurry up, Anthony. I have confidence in you.
Yes. Did you put point one? I did point one by accident. Yeah, I got a different answer. Probably a difference of 10. Or a...
All right, Anthony. I've reached the end of my waiting time. What do you got? Is it No, but you're getting closer. Hey, Dahlia, help him out, please.
I don't know how much help I will be.
That's okay. I believe in you still.
No, like really. I don't know what to do.
All right. Then I'm sorry. I went for your Lifeline, Anthony, and they failed you. So sorry, I watched a stupid show yesterday. What is it? Millionaire, where they have the lifelines. Yeah. So thus, okay, Anthony, I'm gonna help you out. Do you see what I've written here? Hold on, folks. I can't hear. Anthony's a little bit more quiet spoken. Oh, I'm sorry. My handwriting's nasty. All right, so here we go. I made it nice and big. So I'll remind you that there are 3 parts to every torque. Those are the 3 parts for each torque: the torque arm length, the force that you apply, and the angle at which you apply it. So I think I've got these listed wrong between meter stick and torque, but one of these has to be the meter stick, and one of these has to be the 200-gram mass. So this looks like the 200-gram mass. This looks like the meter stick. When I look at the 200-gram mass, actually, no, I think I had them. Yeah, the 200-gram mass, it is 5 centimeters away from the pivot point. So its R is 0.05. I put it in meters. I didn't have to, actually. I could have left it centimeters. I'm just being consistent. And the size of the force applied is mg. I'll point out, I didn't even have to convert it to force if I didn't want to. We're just going to, I mean, all these things are going to be set equal to each other. But either way, 200G is 2 newtons. So that's the 2 here. Now, I have to determine whether this whole thing is positive or negative as well. And I gave you 2 methods to do so. One, you could just look and see what direction it's going to cause it to rotate and decide whether that's positive or negative. That's the way I like to do it. Or you could use the way the book decides, which is to break this up into positives and negatives and do it that way. And looking about the room at all of you who are not writing things down about what to do here, yet will say to me, I didn't know what to do. You should be writing things down. Telling yourselves instructions. Set up a chart. Identify the 3 things that have to be identified. Decide which of each is positive or negative. I mean, do some things like that to help you next time so you can't say, I don't know. Because it looks to me like the 5 is in the negative direction and the weight is in the downward direction. So I got to put a negative and a negative there. Now the meter stick itself, I set the balance point to be, I think the torque arm is 0.1 meters because we said that the balance point was at 49 and then we shifted it to 39. That sounds like 10 centimeters apart. That's 0.1 meters. But I don't know what the force is. So I have to leave a big question mark there. It's unknown. You could put an F there if you'd like. That way it's not like elementary school. It's like, big time high school. We use letters. And then I do positive and negatives again. The 0.1 seems to be in the positive direction. I don't have to put a positive or negative on the letter here. The work will determine that answer on its own. So I don't put a positive or negative there. So now I have to add these up and set them equal to 0. Net torque equals 0. So 0.05 times 2, and they're both negative, so that's going to be 0.1 meter newtons. That's the first one. Plus, that's this one now, 0.1 times F has to equal 0. You solve for F. It should be a super terrible thing here to get this negative number. It's negative 1 Newton. That negative simply means that we think gravity is going to pull down. It's sure better. The answer, though, probably isn't 1 Newton, though. The answer is probably 100 grams. And you should give it an appropriate. And as for the mass of the meter stick, not the weight of the meter stick. And so that's my expectation here. These are called static problems. They're static problems because our object is at rest. And therefore, we can state that the net torque is equal to 0. But there's more than just this. And I want to kind of emphasize something here that I did not emphasize earlier. Static questions have 3 things that have to be done. One of them you've already done earlier this year. They are all net force equals 0 problems. We didn't have to do that here, but that is something that has to be discussed here, that the net force also equaled 0. I never asked it, but I could ask for what the tension in the string was that held the meter stick in place. That's not outside the boundaries of this problem, and you would need to use net force. Static problems also have another part, net torque equals 0. In these problems, you must use both generally to figure out a solution. So let me give you an example of the way I might approach this, say, on a test. And I'm not going to change this very much. I'm kind of going to go the route of reinforcing the example we just had. Imagine you set a board on 2 blocks and you want to walk across it. Perhaps there's something you're trying to get around. So you're going to walk across this board. And let's say the board itself has a mass of 10 kilograms and you have a mass of 70 kilograms. Together, you and the board weigh 800 newtons. It shouldn't be a surprise that together the supports are pushing up with 800 newtons. But do you believe that the supports each push up with an equal amount? I mean, as I walk across, would it seem reasonable that when I'm over here, this support, normal force 1, might be holding more of my weight than this support, normal force 2? When I reach the middle, I think it's probably not unreasonable to think that at this moment, it's split between the two of them. But how about when I'm, over, say, partway towards one, but not necessarily in front of the other? I bet some of my weight's on one, and it's not evenly distributed. This is a statics problem. The net force doesn't tell you the answer. It can't, because these forces are all just up and down. Net torque is required to tell you the answer. In a static problem, the system isn't moving. The third thing that you have to know about a static problem is that there is no real pivot point, but we still deal with the torques. It's not rotating, so there's no real pivot point, but we still have to deal with the torques. So in a static problem like this one, you can pick any place you want to be your pivot point. We'll finish this one tomorrow. Be prepared. First 10 minutes of class tomorrow, right? First 10 minutes of class tomorrow. Okay, Andrew said I had to make it 5 minutes. So first 5 minutes of class tomorrow, we're gonna do something. Thank you, Andrew. You just got me back so much class time.